All right, hi class. This is your chemistry lesson for day 61. It's Wednesday, May the 20th, and we're going to deal with intermolecular forces. Talk about the different types of intermolecular forces. So these are the forces that determine whether a substance is a solid, that is, the molecules stick really tightly together and don't move, or a liquid in which they stick together but they can move around each other, or a gas in which they're completely separate from each other. So that's what intermolecular forces do. So let's kind of summarize this relationship between chemical bonds and intermolecular forces. So we talked about it. There were three types of chemical bonds. Metallic bonds, which are between metals, and I incorrectly stated metal, non-metal on an earlier video, but it is between metals. Okay, so let's summarize the different types of chemical bonds in the relationship with intermolecular forces. So there's metallic bonds between two metals. There are ionic bonds between a metal and a non-metal. And then third, there are covalent bonds. And those are the two strong guys that cannot win the tug of war for the electrons, so they agree to share the electrons. Of those three, covalent bonds form independent structures called molecules. And one molecule can separate from another molecule, or it can stick to another molecule. And so that's what intermolecular forces deals with. So chemical bonds determine new chemical substances by having different atoms combined to form new substances. Intermolecular forces do not create new chemical compounds. They simply determine whether water, for example, sticks together tightly, water molecules stick together tightly to form a solid, or stick together loosely to form a liquid, or don't stick together at all to form vapor. But it's still water, it's still H2O. Chemically, it's the same substance. So this is really more of a concept of the physical structure of water than it is about the chemical structure of water. All right, so the first we're going to talk about are ion-dipole forces. So table salt consists of sodium and chlorine ions, and these are arranged in the lattice structure like bricks in a wall. We talked about that. So when you talk about salt being NaCl, it's not an NaCl molecule. It's a lot of Na ions in a brick wall with a lot of Cl ions, and they're side by side and they attract each other. One of those NAs, which are the ones in blue, do not necessarily belong to one Cl. They belong to all of the Cls that are around them, and the same is true of the chlorides, the Cls. So what happens when water dissolves salt? It doesn't break off into NaCl molecules. Again, it's not a molecular structure. What it does is it pulls apart these ions, so that a chloride ion has more of an attraction to the positive end of a water molecule than it does to the sodium ions around it. Similarly, a sodium ion, the plus signs, have more of an attraction to the negative end of a water molecule than it does to the other chlorides around it, and therefore salt easily dissolves in water. So water is a polar molecule with a negative dipole pointing towards the oxygen atom. That's because the oxygen atom is more electronegative than hydrogen, so it tends to pull the electrons over towards it. It doesn't totally take the electrons away from the hydrogen, it just tends to pull them over to that side. Therefore, the oxygen side of the water molecule is negative, and the hydrogen side is positive. So the negative oxygen side of several water molecules point toward a sodium cation, a positive sodium ion. And you can see that right there where the arrow is pointing. So the sodium is the plus, the blue plus circle, and the negative end of the water molecule is the oxygen side, the red. And so you'll notice that there's several water molecules surrounding that sodium. And that's what pulls it away from the salt crystal. The positive hydrogen side of several water molecules point towards the chlorine. So if you look at one of those green chlorines, you'll see it's surrounded by the positive side of the water molecule. That's the side that the hydrogen is on. And these are called ion-dipole forces because they involve an ion, which is either sodium or chloride, and a dipole, a molecule with a dipole, a polar molecule, in this case water. Okay, both of these effects are called ion-dipole forces. Now, dipole-dipole forces. Dipole-dipole forces attract polar covalent molecules to each other. Hydrochloric acid, HCl, is polar because a highly polar chloride atom pulls the hydrogen electron towards it. So below, the positive hydrogen side of an HCl molecule is attracted to the negative chloride side of another HCl molecule. So in this case, you have two molecules. They're both electrically neutral. They have the same number of protons as electrons. It's just that the electrons are pulled over to the chlorine side of the molecule. So that side becomes more negative. The hydrogen side becomes more positive. And therefore, the hydrogen side is attracted to a chloride in another molecule, and the chloride is attracted to a hydrogen in another molecule. So you don't have ions here. You have two electrically neutral molecules, but both have a positive and negative side to them, and that's called a dipole-dipole. Dipole means two poles, two sides. Water is also creates dipole-dipole force interactions. Okay, London dispersion forces are temporary changes in the polarity of a molecule due to the random movement of electrons. And although it's random, what happens is the electrons tend to get pushed over to one side and therefore creates a polarity in a molecule that's nonpolar. So dispersion forces are how nonpolar molecules attract each other. So when the electron in the hydrogen on the left, so you have the electrons going around and around and around, these are hydrogen atoms, one proton, one electron. When the electron in the hydrogen atom on the left moves to the right, so in atom number 1, the electron is to the right of its nucleus, of its proton. It pushes the second atom's electron, atom number 2, also to the right because the electrons repel each other. If this effect repeats throughout many atoms, it creates a temporary polarity. It's temporary because those electrons could move over to the other side at any time, but it creates a temporary polarity that attracts atoms to each other. So what you have is you have the electron in atom number 1 pushing the electron in atom number 2 over to the right, and what you also have is the polarity of that electron in atom number 1 being attracted to the nucleus of atom number 2. So two things are happening. The electron in atom number 2 is getting pushed to the right, and the electron in atom number 1 is being slightly attracted, not a very strong attraction, to the proton in atom number 2. You can then have that process repeat. Atom number 2 pushes the electron in atom number 3 over to the right, and it's attracted to the proton in atom number 3. So what you see is the electrons are all pushed over to one side. And if you have a large number of atoms that are doing that, that'll make the right-hand side of that particular molecule, assuming all those atoms are in the same molecule, that'll make the right-hand side of that molecule tend to be more negative, and the left-hand side tend to be more positive. Again, it's not a permanent dipole because those electrons could switch and go to the other side at any time, but it creates a temporary dipole. So this is a very weak type of intermolecular force. So London dispersion forces are small but can produce stronger attraction between large molecules with many electrons. So a very small nonpolar molecule is methane gas, CH4. It is nonpolar, it's symmetrical, the electrons are spread out evenly around that molecule, and therefore it's not polar. It is nonpolar. But it has very weak London dispersion forces because it only has 10 electrons. Methane has a very weak London dispersion force and is not attracted to other methane molecules. That's why at room temperature, methane, which is natural gas, is in gas form. The molecules will completely be spread out. Now, let's look at one that's a bit bigger. It's also a hydrocarbon. It has just carbon and hydrogen in it, but this is octane. It's C8H18, and it has 66 electrons. Now, that's enough electrons. This is strong enough to make the octane a liquid with other octane molecules. So if those 66 electrons all get pushed over to one side, then that'll make that side of the molecule negative and the other side will be positive. That will create a strong enough London dispersion force to actually have the molecules stick together, and that's why at room temperature octane is basically gasoline, and it will be liquid form just like it is in the gas station when people pump gasoline into their car. And finally, let's look at an even bigger molecule. And you see that's a very long hydrocarbon. Again, all three of these molecules are just carbons and hydrogens, but this one is very long, and it's called paraffin, and that's candle wax. And it's C40H82. which if you count up all the electrons, it has 322 electrons. This many electrons form strong enough attractions to make paraffin a solid at room temperature. So as you know, candle wax is solid at room temperature. It just takes a little bit of heat to start to melt it down, but nonetheless, at room temperature, normal room temperature, it will be a solid. And this is strictly because all the electrons get pushed over to one side of that molecule, and they push all the electrons in the next paraffin molecule over to the other side, and that continues on until the molecule has strong enough attractions to form a solid. Okay, the shape affects the strength of London dispersion forces also. Longer, flatter hydrocarbons such as N-pentane on the left form stronger London dispersion forces than round neopentane molecules on the right, because they fit together tighter with less space. So you can see how the molecules on the left, you could kind of just stack them neatly on top of each other, and therefore they will be tighter together and form a stronger bond. Whereas the ones on the left are almost kind of spherical shaped, and it's very hard to get them to fit together very tightly. All right, hydrogen bonds. Hydrogen bonds occur when a hydrogen atom is bonded to the three most electronegative second row elements. In fact, they're the three most electronegative elements on the periodic tables: nitrogen, oxygen, and fluorine. So hydrogen bonds can only happen when you have a hydrogen attached to either a nitrogen, an oxygen, or a fluorine. So when oxygen pulls the electrons of a hydrogen towards it in a water molecule, these are water molecules you're looking at, an exposed hydrogen nucleus, which is just simply a proton, is left exposed. This proton is attracted to the lone pair of another molecule of nitrogen, oxygen, or fluorine. The hydrogen atom has a fairly strong attraction to the other atom, though it is not nearly as strong as it is to its own covalent bond. So it's been a long time since we've talked about Lewis structures. So the two electrons that are attaching the oxygen to the hydrogens, and you'll notice I drew the hydrogens not with an H for hydrogen, but as pluses to indicate that they are protons. They're positive charges that are sticking out there. The electrons that are bonding the oxygen to the hydrogens are called bonding pair electrons, and the two that are out there by themselves, not on each of those molecules, not bonded to anything, are called lone pairs. And so what happens is the hydrogen on one water molecule, the proton, can be attracted to the lone pair of another molecule of either oxygen, nitrogen, or fluorine. In this case, it's oxygen. So where you see those dashed arrows, that's where the protons could be attracted to another molecule. Again, that bond between those dashed arrows and the lone pair, between the proton and the lone pair of the other molecule, is not nearly as strong as its bond with its own oxygen atom, and therefore that hydrogen, that proton, will not get pulled away onto the other molecule. It's simply going to be attracted to it. And so that's what a hydrogen bond is, because it only applies to hydrogen atoms attached to either nitrogen, oxygen, or fluorine. Now you can mix and match hydrogen bonded molecules. So for a hydrogen bond to occur, a hydrogen atom must be attached to a nitrogen, oxygen, or fluorine, and must be attracted to the lone pair of another nitrogen, oxygen, or fluorine. But as I say, you can mix and match. So look at the two molecules on the left. Those are both water molecules. They're H2O. And you can see that the hydrogen on the left side of the top molecule is being attracted to the lone pair of the oxygen on the bottom left side. Now, in the middle there, you have a hydrogen atom on a water molecule, and it hydrogen bonds with the lone pair on a nitrogen atom. So that nitrogen is part of an ammonia molecule, NH3. And so you can mix and match. You can have the hydrogen on an oxygen be attracted to the lone pair on a nitrogen. And finally, here you have a hydrogen atom on a nitrogen being attracted to the lone pair of a fluorine atom. So it bonds with the lone pair of the fluorine. The reason that it has to be one of these three central atoms, nitrogen, oxygen, and fluorine, is because they are the most electronegative, and so they pull the electrons the furthest away from that proton, from that hydrogen nucleus, and therefore it really makes that hydrogen nucleus seem more positive to other atoms, and therefore it can be attracted to the lone pair of other atoms. So it takes a strong electronegativity to really expose those protons and really make them kind of stick out and show their positive charge. So hydrogen bonding works because nitrogen, oxygen, and fluorine pull the electrons away from the hydrogen so completely that an exposed proton is left sticking out from the molecule. Okay, now the hydrogen bonds of water, H2O, are stronger than the hydrogen bonds of ammonia, NH3, or hydrofluoric acid, HF. Why would that be? Over on the left, there's one hydrogen on a water molecule for each lone pair. So you'll notice there's a 2-to-2 match right there. There's 2 protons on one of the water molecules that's connecting with 2 lone pairs. So it's a perfect match. Everybody has a dance partner. Okay? If you have the same number of boys as girls at the dance, everybody's going to have a dance partner. And so water has a much stronger bond because that perfect match between number of protons and number of lone pairs. If you take all the water molecules in the in that cup of water, there will be a perfect match of 1-to-1 or 2-to-2. Now ammonia has only 1 lone pair for every 3 hydrogens. So look at the structure of the ammonia. It has 3 protons and only 1 lone pair. So only one of its 3 protons can go off and attach to the lone pair on another nitrogen molecule. And so therefore it's like you had 3 times as many boys as girls at the dance, then a lot of the boys won't have a dance partner because there's just too many boys. And that's kind of what's going on here. So no lone pairs for those 2 to match up with. Finally, hydrofluoric acid has only 1 hydrogen proton for every 3 lone pairs. So that's the opposite situation. That's like you have 3 times as many girls as boys at the dance, so a lot of the girls won't have somebody to dance with. And there you see there's no hydrogen to bond with those 2 lone pairs right there, because each fluorine only has 1 hydrogen atom and 1 proton. So water hydrogen bonds most efficiently and has the strongest hydrogen bonds. So here's a summary. Generally, the following is the order of strength of different intermolecular forces from weakest to strongest. London dispersion forces are the weakest because they consist of temporary dipoles. All molecules have London dispersion forces, but they really only become prominent in nonpolar molecules because nonpolar molecules don't have dipole-dipole, they don't have ion-dipole, and they don't have hydrogen bond forces. And London dispersion forces are strongest in large, flat, nonpolar molecules. Dipole-dipole forces are next because they consist of the positive-negative ends of electrically neutral molecules. So the hydrofluoric acid was an example. Water is another example. Water is polar and has positive-negative ends. Ion-dipole are stronger because they contain a fully charged ion, such as sodium, or the sodium ion or the chloride ion. So that's a fully charged ion, and that's connecting with a dipole molecule such as water. And finally, hydrogen bonds are considered, they're really not bonds though, they're really forces. They're not chemical bonds. So it's kind of a poor name for them, but that's what the name they gave it. So hydrogen bond forces are the strongest. Hydrogen bonds formed by water molecules being stronger than other hydrogen bonds formed by water molecules are stronger than other hydrogen bonds, those formed by nitrogen or fluorine. Okay, so that's the end of our lesson on intermolecular forces. I have a short worksheet in there. Again, the whole thing hopefully won't take you more than a half hour to do this. Get caught up on your other assignments. This is due on Tuesday, May the 26th. And I want everybody to get caught up on their assignments and really get ahead. There's no solutions video to this because all the answers to the questions in the assignment are in this video. So just watch it carefully with the assignment by your side and you can get these answers on. Okay, I hope to hear some of you tomorrow, Thursday. I'm recording this on Wednesday morning, and I had a few people show up for our Wednesday meeting. I hope to hear you Thursday, have you here Thursday. You do get 25 points extra credit just to log in and say hi and let me know how you're doing. Okay, so I hope to hear from you tomorrow.